What we were doing is talking about this transport equation. We have a probability distribution for the position and the velocities of molecules, and the situation is not equilibrium, and in principle del F del T changes, that is F changes, so there is a del F del T which is the partial at fixed R and V, and then there is a V dot, the F can change as the particles move out of a given volume just because they have a velocity. And then there is the movement because there can be an external force, and this is equal to the rate of change due to collision, and this is equal to integral. So F of R, there's a d3 v1, and there is F of R v2 t F R v3 t minus F R v1 t F R v t. So that's the rate of change by collision. So this is the total derivative and the change due to the time rate of change due to the collision process. This the collision process is elastic collision. V and V1 colliding to go over to V2 and V3. That's the loss that you see over here. V and V1 colliding and getting out of the V getting out of this its box, and the reverse, that V2 and V3 can collide and can get you into the V slot. So that's the that explains the sign. And what we had seen last time, that the equilibrium means no external force and if there is no R dependence, if there is no R dependence, then this term is gone, and we have a situation where it is F1 is F2, F3, and from the collision invariance, taking a log and noticing that log F is to depend on the collision invariant, we came up with n equal to m2 pi kt to the power 3 by 2 e to the power minus mv squared. So that's the setup. And with that now, we are in a position to talk about actually disturbing the equilibrium. So, which is the most natural thing, I mean, the fact that one speaks and somebody else can hear is because there is a disturbance of equilibrium. The fact that somebody else who is very far away can't hear what is being said is also a fact of not being in equilibrium. That is, the sound that you produce because things are not in equilibrium decays, the intensity goes to zero if you are very far from very far away, and there it is a new equilibrium for whoever is there, where this sound has decayed and is not causing any disturbance over there. So equilibrium and being out of equilibrium, and then the out of equilibrium being in out of equilibrium, and the decaying of the out of equilibrium state, all a part of study of this Bose transport equation, and which means that we have to get a handle on how to work with this. So the handle, as we started out the day, is almost always when one is given a complicated, difficult situation, one resorts to perturbation theory. So you write FRVT is F equilibrium, which in this case is just a function of V, plus a delta F, which can be a function of R, V, and T. And as the way you do it is actually the right best way to write this as is to write it as a 1 plus. This makes life easier. So F equilibrium times 1 plus delta F. It's just a question of defining delta F with the F equilibrium thrown in. It does helps in the algebra. So all right, and then we need to linearize. So you go to this side over here, and you pick up delta F, del T. There is the F equilibrium sitting out here. And then there is, so the this term over here, F equilibrium will be sitting out of everything. So when I do this, it is going to be V dot del F, del R of delta F. I'll take F equal to 0. So no external forces. So that's the left-hand side. And that's equal to integral d3v1. And then it is F0 R V2 F0 R V3, which is the same as F0 RV and F1 R V1. So the equilibrium values, I mean, that is what F1 is F2, F3. So whether I take out, this is F2, this is F3. And equilibrium, these are the same. So I'm writing this into, it is 1 plus delta F V2 plus delta F V3, linearizing in the delta F's, 1 plus minus 1 minus delta F V T minus delta F V1 T. And so this is equal to integral d3v1 and it is F0 RV F1 RV1 and into delta F V2T plus delta F V3T. It's all minus delta F VT external forces T, and that's that. There is a sigma, missed it, sure. Over? No, D3V has cancelled because it is F over here, no? I mean, if I integrate out over V, this is F of RVT, can't integrate out, right? There's the D3Vs have to cancel from this side and that side. It was the number, maybe it is the change in number. Change in number included a D3V, D3V1, and then this, everything. The number changing to F removes the D3V. Huh. I mean, there should have been, I mean, yeah. From number, I went to, it was number in, number out. And then from the number in, number out, when I change, the D3V moves out. বাঁদিকটা দেখো, বাঁদিকটা ভেলোসিটির ফাংশন তো ডান দিকে যদি আমি ভেলোসিটিটা ইন্টিগ্রেট করে দিই তাহলে তো আর কিছু থাকবে না পড়ে, রাইট? সো এটা যখন আমি এটা ক্যালকুলেট করছিলাম, আমি একটা ভলিউম এলিমেন্ট নিয়ে নাম্বার ইন নাম্বার আউট এই করে করছিলাম, এন ইন এন আউট। এখন এনটা কি? এনটা হচ্ছে ইন্টিগ্রাল অফ এফ d3v and d3r. So এটা n হচ্ছে এই ইয়েটা। So n in n out there is a মানে there is a d3v. এখন এই d3v টা যখন এই n in n out থেকে I have changed it to f in f out, তখন the d3v টা দুদিক থেকে কেটে গেছে। হ্যাঁ, so তাই এটা কাটতে হবে, কারণ তা নইলে পরে এইদিকে মানে this becomes a number, আর কিছু হয় না। Whereas it is f of v is changing with time, and there has to be, this side has to be dependent on v. It's entirely possible যে আমি আগে d3v লিখেছি আর ওটা ক্যান্সেল, মানে n থেকে f এ গেছি without cancelling the, but v minus v1 ছিল, right? Sure. Sorry. Sorry. মানে all the things that, yeah, sure. ঠিক আছে। আর সেটা তো এই d3v1 এর মধ্যে দিয়ে চলে আসছে। আর আচ্ছা, সিগমা ডি ওমেগা, সিগমা ডি per unit solid angle। per unit solid, the sigma is per unit solid angle, and therefore the point is if it is per unit solid angle, I will have to do over all solid angles there will be. There is an integral of this.
into RHS of the RHS of the equation is V2, V3 and VR. So it is velocity function. Left hand side. V1, V2,
V1 না কিন্তু লেফট হ্যান্ড সাইডে থাকবে কি করে লেফট হ্যান্ড সাইড তো ডিটারমিনড অনলি বাই ভি এর মানে এফ অফ ভি এর চেঞ্জ দেখছি না লেফট হ্যান্ড সাইডে কেবল এইটা চেঞ্জ করছে ইটস এ ডি অফ দ্যাট এই সাইডে এসে ইন্টিগ্রালটা ভি এর উপর ইন্টিগ্রাল হবে না ইট ইজ অনলি v1 আর v2 আর v3 তারা তো ডিটারমিনড বাই v and v1 হ্যাঁ So it's a collision process, no? Collision to elastic collision tells you the V2 plus V3 or V1 plus is V plus V1 or V2. Yeah, right. The union. Right. So, so that. কি হচ্ছে না কোনটা এইখানে ও ডেল্টা এফ ডেল্টা এফ আর থাকে জাস্ট লিখিনি মানে মানে আর এটা যদি মানে ইয়া হয় আর কিসের ডেল্টা এফ তো আর ডিপেন্ডেন্ট হবে না হ্যাঁ না কিন্তু আমার এফ তো অলরাইট এফ is if there is no external force you are right I don't expect f of f will be a function of r all right because but the point is that simply because there can be a flux of particles because of the collision you may be taking particles out of this box so the local f might change because there is this term is not zero that when this I can your f can simply be a function of r and v and this r and v makes it but if it is a rvt that I am looking at for the point is immediately that df dt can be a function of it is a partial derivative of this plus a v dot del f del r. So there can be the f can there f is as a function of r can still be there and it is because of the velocity it is possible simply because of the intrinsic velocity some molecules may be leaving this box d3r
f of r distribution
f of r distribution not in equilibrium equilibrium এ নেই কিন্তু যখন it is not in equilibrium so এইটাকে ফেলতে পারছি না কারণ the point is যে যখন equilibrium নয় তখন ওটা r এর সাথেই হতে পারে সেটা has to relax and that is what we will see কিন্তু the point is যে that can be there but this if the external force is absent certainly zero কিন্তু ওইটাকে ইয়ে করতে পারি না।
Effect on the del F by del T হবে। Just ঠিক আছে, just like-
হুম,
If F by M is equal to into del F by del T হবে।
কোনটা এইটা?
হ্যাঁ, এটা del F by del T।
Yeah, sure. Sorry. Absolutely. ঠিক আছে। So that's the setup. So now I have the equilibrium distribution is Maxwell-Boltzmann, which we, and now I suppose I disturb the equilibrium slightly. What is going to happen? There is no external force, and I have to linearize, and as I linearize, I erase this line certainly at this point. And the linearization leads to del F del T plus V dot. So let me write, all right, I can erase the previous line as well. So there is this, and I can erase this one, and this is gone, and this is gone, and this is equal to integral d3 v1 f 0 r v f0, where is the what happened? There were কোথায় গেল? There's f0. Why did I? Acha, oh, f0 f1, sure. All right, f0 f1. That's the, all right. That was fr v1, and I have this delta f r v v2t delta f. So let's call it delta f3 delta f delta f minus delta f1 delta v2.
Delta F plus delta F.
So that's that. Sure. Very good. I've got, oh no, it's not right. Sorry, there was a f. There is a f0 here. There is a f0 here. So the f0s have to cancel. So f0 cancels, f0 cancels, f0 cancels. Now looking simpler. So come a long way. R v1, this is f0 equilibrium. It's v1 here, and then I have delta v2 plus delta f, sorry, v2 plus delta f v3 minus delta f v minus delta f v1. Good. Okay. Good. All right. So now what can I let's change notation a little bit so that I don't have to write delta f of v. I'll call it psi of v. So del psi del t. This is, I mean, just cosmetic, but keeps psi. This is equal to integral d3(1). There is f(0) of r v1 and I have psi v2 plus psi v3, which is essentially psi v1. There is sigma, there is the sigma, there is v minus v1, and the, yeah. এখানে দুটো f0 ছিল, তার মধ্যে একটা f0 মানে এইদিকে যখন এই fটাকে লিখেছিলাম f0 into 1 plus ডেল্টা f, তাই জন্য যখন এইখানে ডেল্টা f টি, তাহলে একটা ডেল্টা f ওর সাথে লেগে আছে। সো সেই f0টা একটা f0 কে ক্যান্সেল করেছে, নেমলি দ্য f0v। হ্যাঁ, f টাকে তো লিখছি না যে f0 ইকুইলিব্রিয়াম f into 1 plus delta f, which is the non-equilibrium part, সেইটা করায় এইখানে মানে এটা এই যে এই ডিস্ট্রিবিউশনটা is মানে এখানে দুটো f বেরিয়ে আসবে না, দুটো f ছিল, সো তাহলে এখানে একটা f বেরিয়েছিল f0 আর v বেরিয়েছিল, f0 আর v1 বেরিয়েছিল, এদিকেও f0 আর v আছে, এখানেও f0 আর v আছে, কারণ ইকুয়েশনটা এই। সো তাই জন্য f0 টা কেটে গেছে, f0 আর v টা কেটে গেছে, আর v1 টা রয়েছে। So let's look at, so how am I going to go about this? The way I'm going to go about this is to say that this term is small. So perturbation theory, as I said, is what one is going to use. So perturbation theory, so what is meant by this term is small. So I'm going to say that this is small. So small in what sense? Small means, so this is the term which is, the potentially problematic, because this is where the R dependence comes. If I did not have this term over here, I could just say that there is not going to be any R dependence in these things over here, and everything will just be a function of V. This is there, and we know what the equilibrium distribution is, and that's it. But now if I have the equilibrium, if I start with the equilibrium distribution, which does not have any R dependence, it is this quantity over here which can lead to an R dependence for me. So now what kind of, because this whole the psi which I'm going to talk about has to get into this. I mean, you are talking about F is equal to F0 into 1 plus delta F. This delta F is what has become the psi, and the whole new part of delta F is that it is a function of psi and possibly V. And now, so now you focus on, so therefore it has everything to do with this, the smallness has to do, every perturbation theory has to do with this term over here. So what am I, suppose this term is not there. If this term is not there, then I say that del psi del t is equal to this, and you are going to, I mean, there are, it's the R. Suppose the this del psi del r is not there, and I'm supposed to look at this quantity over here. Well, then del psi del t is this, which is has and the point would be that look, with time you look at this and you say there is going to be the zero of this is going to get me the I mean, there is a fixed point, essentially del psi del t is equal to 0 if all the psi's are equal to 0, and that's a state which is going to be, I mean, that's a trivial solution which is going to be the answer. So, but it is the whole business of this is going to, hinges on that there is this part over here which brings in this non-triviality that there is a R-dependent psi over here. A psi which is just dependent on V could have been simply absorbed in this F0 as a. So I want to know, I mean, so how do I make del psi del R small? Del psi del R small means psi is slowly varying, right? If slowly varying with R. If psi is slowly varying with R, then del psi del R is going to be small. Next, what kind of a psi I can talk about? I can talk about the psi of R that I can talk about is, you think of it in Fourier space and you say that, look, psi can be like e to the power I k dot R, and this would be the spatial dependence of the psi R. There can be a V dependence, but then the important thing is that it is the del psi del R which has to be small, and it is going to be the del, and therefore I can take an approximation where psi is of the form e to the power ik dot r. Everything has a Fourier transform, and therefore you talk about, imagine the Fourier transform and focus on the part of the Fourier transform where this k is small, that is the long wavelength part is only important. So it is k small.
Why we are choosing this form of the response?
Huh?
Why we are choosing this form of the function?
Anything, look, I mean, it's a linear equation in psi. So I can always do that. And it's k is small. So linear in psi, I can always try a solution which is exponential in r, and therefore, I mean.
And what about t?
The t dependence right now I'm in just so there is going to be a e to the power ik dot r, and there would have to be a t dependence which I would have to put in. So it's the spatial part which is this. So all right. So I have now comes the question that all right, this I will treat as a perturbation. That is, this term is supposed, so therefore the bulk is, the main term is this del psi del t is equal to, let's say, some k0 psi, which is equal to, call it, it's linear, so call it k0 operating on psi, and then this is d3v1 f0 and psi r, and this is, so the psi 2 is what I called it, right? I mean, so call it psi 2 plus psi 3 minus psi. So that, I mean, there are the sigmas and the v minus v1. Good. So now you notice that k0 psi has a solution where, I mean, there is a k0 psi has essentially 5 situations where the answer is k0 psi is equal to 0. So there is this del psi del t. I mean, so if I look at this as an eigenvalue problem, k0 is some operator acting on psi, then k0 psi is equal to 0 for 5 possibilities of psi. So I'm focusing on this part over here. I have an eigenvalue, I'm solving a problem for find psi such that k0 psi is equal to this. So I'm solving that part of it, that k0 psi equal to this. And I find that there are 5 solutions, psi equal to constant, k0 psi is equal to 0, psi is equal to v square, k0 psi is again equal to 0 because kinetic energy is conserved, and vx, vy, vz. So K0 psi equal this is the by definition the K0 psi operator, and there are so if I think of K0 psi, if I think of K0 psi, diagonalizing it and writing it as some lambda times psi, then I have found 5 eigenvalues. So this is a linear operator which I can diagonalize, and I have found 5 eigenvalues for which are zero.
5 states for which
Five psis for which the eigenvalues are 0. So 5 times degenerate 0 state. হ্যাঁ মানে আমার 0 eigenvalue আছে কি নেই, সো আমি এটা দেখতেই পাচ্ছি যে সাই 5টা সাই আছে, যার জন্য এইটা 0 k0 psi equal to lambda psi হিসেবে লিখলে lambda is 0 for 5 psis. Now the point is, the next point, that are there psis for which lambda is negative? Huh. So are there, so that's the next important step, that can I have psis for which, so I need to take a scalar product. So I want to consider psi K0 psi integral d3v. So these are all functions of v. I mean the psis are, so they are functions of v over here, and I want to do the psi K0 psi d3v. When all right, I mean these are essentially all real, but I mean if I wanted to, I would be careful and writing, I mean the কোয়ান্টাম না না কোনো কোয়ান্টাম কিছু নেই। না না সাই স্টার তো সাথে কোয়ান্টামের কিছু ব্যাপারই নেই না, মানে এটা তো একটা ইয়ে, ইজ ইট আ কমপ্লেক্স ভ্যালুড ফাংশন অর নট, তাই না? মানে আমার আইগেন ফাংশনটা যেটা বেরিয়েছে সেটা একটা কমপ্লেক্স ভ্যালুড ফাংশন অর নট। আমি e⁴ এর কথা বলছি, সো এইটা ইজ আ কমপ্লেক্স ভ্যালুড ফাংশন, কিন্তু I can also write it as cos kr and sin kr in this case. মানে না হ্যাঁ রাইট, nothing quantum about it. So so all right, so so now the point is that is lambda equal to 0 the lowest eigenvalue of this so because it's all very important. It's why is it so important? It is important because in general the delta f that you are going to write down is going to be a sum over the eigenfunctions that I'm going to find over here. Those eigenfunctions would be the basis for writing down any particular psi that you want. So therefore I need to know, suppose I am sure that there is no, the answer for this the time dependent part of psi. It's a linear equation over here. So psi is certainly be like e to the power lambda t, right? I mean, these eigenvalues, del psi, del t is k0 psi has this. So therefore, the lambda is telling you about the growth of the time growth. So it is if lambda has this, I mean, positive, that is, if I write this as minus lambda put in the appropriate whatever. Yeah. So the point would be that if my lambda, if psi written as e to the power minus lambda t, all the lowest possible eigenvalue is 0, real, this can have real and complex. This is no Hermitian property, nothing. So eigenvalues can be real. So what I need to ensure that the a real part of this can, if that is never always that if that is always positive, then the psi can either decay with time or oscillate in time. Get the point? Huh? Also, either oscillate in time or decay in time. Huh, oscillating decay to sure. মানে আমার কথাটাকে বেশি জোরে শোনা যাবে না। Yeah. It is oscillating decay, but the important thing is যে এটা grow করতে পারবে। I need to ensure that there is no positive real part of lambda. হ্যাঁ, বাড়া যাবে না। হ্যাঁ। So therefore, what is lambda? Lambda is the inner product of psi with k0 psi with psi divided by the inner product of psi with psi. Right? So everything hinges on psi k0 psi. So this F0, what is the here? All right. So I'm looking at psi k0 psi and integral over. So it is, I'm looking at this side over here, d3v1. Then there is this f0, and then I have psi and psi2 plus psi3 minus psi minus psi1, and there is this sigma v1. So, all right. Step one, write this with psi and psi1 interchanged. So psi and psi1 interchanged, then all that will happen is it is still d3v1. It's still whatever this f0 is, but it is psi1 over here, and then it is the same. কোনগুলো? Psi f0, this is psi, and then there is the set of these psis k0 K0 psi has this is the psi. আর এটা হচ্ছে K0 psi. So this is now, I mean, I have interchanged psi and psi1. So psi has become psi1, and it is psi2 plus psi3 minus psi1 minus psi, and it is the same sigma v minus v1. Huh. Now I will go and interchange the 1 and 2, 0 and 3, or say, let's say 0 and 2, 1 and 3. 0 being the one which doesn't have a, right? I'm going to interchange this and this and this and this. Then it is going to be D3 V2 D3 V3, right? F0, which is just the weighting factor, but then psi1 has become psi3 or psi2, whatever. No, it is a psi which has become, I'm doing the interchange over here. Psi has become psi2, and inside here psi1 has this is, so it is psi plus psi1 minus psi2 minus psi3, right? And it is sigma, the same sigma, because sigma has all the reflect properties under interchange, and v2 minus v3, which is also v minus v1, elastic collision. All right. All right. So then comes this, and now comes the other one, the last one. When I interchange, I mean the opposite, that is psi with psi3 and psi1 with psi2, right? And that is going to be the same, and D3V2 is the same as D3V D31, and therefore the last one is going to be once again D3V2 D3V3, and it is going to be this F0 over here, and it is psi3, and it is psi plus psi1 minus psi2 minus psi3. All right. So this is D3V1. This is D3V1, and you are looking at all these. I mean, the V minus V1 in all of them, and the same sigma for all of them. And this is what is psi K0 psi integral D3V. So what I do, all of them are equal, so I can add them and take divide by 1/4. So it is 1/4, and I add them, and it is going, the first step is psi2 plus psi3 minus psi1. The next one is also psi2 plus psi3 minus psi1 minus psi, and then it is your psi plus psi1 minus it's the psi plus psi1 minus psi2 minus psi3 That's the change over there. And there is this psi plus psi 1. Right. So I'm adding. So there is, this is the same as this, which is psi plus psi 1 here. And this and this has a psi 2 and this has a psi 3. They add, but then they have a minus sign. And therefore, what you have over here is psi 2 plus psi 3 minus psi 1 whole square. Sigma V minus V1 F D3V D3V1. Get it? Get the point? Huh? Therefore, it's positive definite because of that square. And therefore, this is greater than equal to 0. Huh. So that's the big step. You have shown that this operator K0 psi, the operator K0, this cannot have any negative eigenvalues. Huh? The ground state is 0, 0 eigenvalue, 5-fold degenerate. All right. So that's the. So, I mean, now we are through. I mean, this was the big demonstration over here, which is the vital issue that you have. All right. So now, so what am I doing? I'm solving the Schrödinger equation. Del psi del t is equal to K0 psi minus I, this perturbation, which was del r of V dot del r of f, delta f, right? That is what, this is what I had to solve. What I have is that this I will, this we said I would use as a perturbation, and delta f is your, this delta f was the psi e to the power I k dot r with the psi as a psi of v, and so therefore this is K0 psi minus I k dot v times delta psi. Correct? So what you have is del psi del t equal to this, and then there was this psi form of v dot del fr, which is my delta f is like psi e to the power I k dot r, so it is minus I k dot v delta psi. This we said we are going to treat as a perturbation because k is small. And this is the big part. This is the unperturbed part of your system. So this is like a Schrödinger equation without the I, and it is del psi del t is K0 psi, that is the big part. And in this big part, I have just shown that there is the lowest eigenvalue del psi del t is equal to K0 psi. Lowest eigenvalue is lambda equal to 0 with 5-fold degeneracy. All right, get it? Huh? So, so now recall degenerate state perturbation theory. What's the answer on that? You have to take the matrix that you have over here and get the matrix element of this. So matrix element the matrix element of so take k in the z direction, k vector in z direction, that's entirely up to me. So it is I forget the minus sign, k z v. So the operator I k z v z, I want the matrix elements of that. The this ground state is 5-fold degenerate. What are the eigenvectors? Eigenvectors are the 5 conserved quantities Vx, Vy, Vz, V square, and 1, which is a constant. I mean, constant. So I have to form a 5x5 matrix of this KZBZ. Acha. The best thing, I mean, you have to choose things with care when you are doing the calculation. For V square, and instead of V square, one is it's easier to work with V square minus the average taken out. The average is 3 kt by m, right? So take out the average. That makes, I mean, so these orthogonality is that is Vx, Vz would not have been orthogonal to this. There could have been problems with orthogonality of orthogonality of V square with 1. That orthogonality is taken care of that by saying that it is V square. My eigenfunction is not V square, but it is V square minus average V square. Then it is orthogonal to 1. See, I want to work with, I'm doing degenerate perturbation theory, right? I have 5 eigenvectors. So I have to diagonalize the matrix element of this perturbation Hamiltonian. The matrix, that matrix, the 5x5 has to be diagonalized, right? So if it has to be diagonalized, the best way to work for me, well, the best way to work, I have to find these the eigenvectors. I want the eigenvectors to be mutually orthogonal. My eigenvectors by inspection are Vx, Vy, Vz, V square 1. But they are not mutually orthogonal, but because V square is not orthogonal to it. I have to do my 0th order answer. The 0th order wave function is F0 is Maxwell-Boltzmann. Right? So it is e to the power minus V square. So e to the power minus V square has a matrix element between 1 and V square. But I'm always free to take a linear combination of these things. And that's all. So V square I will take as the combination of V square and 1. Which is V square with a coefficient. The coefficient I choose as V square average. So V square minus average V square is my eigenvector. Now it is automatically, so I work with the eigenvectors V square minus average V square and 1. Yeah, so this is a mutually under the wave function e to the power minus V square or weighting factor of e to the power minus v square over kt. All these vx is perpendicular to vy, perpendicular to vz, perpendicular to this and this. And similarly for the others are trivial. The only non-trivial case was this, and this is now by definition. কারণ ওয়েট ফ্যাক্টরটা হচ্ছে e to the power minus v square, তাই দিয়ে মানে স্কেলার প্রোডাক্টটা তো is being defined as scalar product is যে একটা ফাংশন অফ v, এখানে যদি থাকে f1v আর f2v, তাহলে আমার এক্সপেকটেশন ভ্যালুটা তো ম্যাক্সওয়েল বোলসম্যান ডিস্ট্রিবিউশন দিয়ে, মানে all this is what am I calculating is f0 1 plus delta f. f0 টা তো হচ্ছে e to the power minus mv square over 2kt, Gaussian distribution. So Gaussian distribution এ মানে এবার যে কোনো f1v আর f2v scalar product হচ্ছে e to the power minus mv square over 2kt f2v integral, that is the definition of the everything is defined with a weight factor of e to the power. So এখানে f1 টা যদি হয় 1 আর f2 টা যদি হয় v square, তাহলে the answer is not 0. হ্যাঁ, কিন্তু এইটা নিলে পরে v square average is calculated with this distribution, and therefore these I have 5 mutually orthogonal wave functions. And therefore all my rules of second order perturbation theory work. I need to write down the 5 by 5 matrix যেটা দিয়ে এটা কাজটা হবে. All right, so 5 by 5 matrix in round 1 first order, vx and vy are not going to play any role because they have zero overlap with all the others. So you look at the structure over here. You look at the structure of this matrix. And it is going to be 0 everywhere through except this 3 by 3 part. Right? So obviously there is going to be an entry over here which is decoupled from. Yeah, I mean that is when I do vx into vx into then the distribution that is non-zero. But everything is 0 here and everything is 0 here. Huh? Vx does not overlap with Vy. Na? These are all orthogonal. একটা এই ইন্টিগ্রালটা তো 0, Vx vy e to the power minus v square d3v, that is equal to 0. Huh? Huh? Diagonal, no, diagonal kishe. There is many vz with 1 or v square minus v square. Yeah, man, there is a perturbation, na? See, আমার এই perturbationটা তো হচ্ছে vz. So vz এর matrix elements লিখতে হবে না? So vz এর matrix elements লিখতে গেলে পরে কেবলমাত্র এই তিনজন হচ্ছে any matrix element of vz with vx vy সেগুলো তো 0. So all that I need to do হচ্ছে যে এই সাবস্পেসটায় vz এর matrix element দেখবো. and vz এর matrix element কাদের কাদের মধ্যে আসবে না it can all the diagonal elements গুলো কিন্তু 0 হয়ে যাবে, right? So I take vz and form diagonal, I mean because that is always মানে এই 3/3 টা has to have diagonal element 0, হ্যাঁ কারণ yeah, so vz এর কিন্তু off diagonal elements not 0 কারণ vz এর matrix element between the vectors vz and 1 that is non-zero. Between vz and 1 a non-zero, 1 are vz non-zero. Huh? No, vz তো হচ্ছে আমার vz is the I am considering all যে vz এর এই দিকে একটা ওয়েভ ফাংশন psi1 এদিকে একটা ওয়েভ ফাংশন psi2, সো সেইটা হতে গেলে পরে vz এর যে ওয়েভ ফাংশনটা নিচ্ছি সেই ওয়েভ ফাংশনটা এইখানে আর এইখানে এটা যদি থাকে v square minus average v square আর 1 তাহলে সেটা 0, হ্যাঁ কিন্তু যদি সেটা থাকে যে এই দিক মানে এর যদি all the diagonal elements have to be 0, কারণ diagonal মানে যখন diagonal element এ 0 হয়ে গেছে they are all মানে একটা vz is odd কিন্তু diagonal মানে হচ্ছে যে মানে স্কয়ার এগুলোর, সো সমস্ত বেরিয়ে গেছে, হ্যাঁ আছে কেবল কে আছে কেবল হচ্ছে যদি vz এর সাথে যে ম্যাট্রিক্স এলিমেন্ট গুলো আর অফ দ্য ফর্ম যে vz is sandwich between 1 and vz, হ্যাঁ তবেই কেবল, কারণ তার উত্তরটা হচ্ছে vz স্কয়ার into with the weight factor. vz into এখানে the diagonal elements have to be 0, হ্যাঁ বুঝছো না, সো থাকবে দুটো off diagonal elements which are of this kind, right? So দুটো non zero eigen value হবে আর তারা will be plus minus I, হ্যাঁ মানে এটা কোষে obviously দেখে নেবে যে there will be two eigen values and so you are looking at here যেখানে the determinant which is looking like এখানে just lambda 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 বসে আছে কারণ the diagonal elements গুলো তো are 0, so I'm trying to find the eigen value of this eta আর কি, so then I'm diagonalizing this I'm diagonalizing a matrix which looks like তিনটে 0 আর এক দুটো জায়গায় like this and this দুটো এলিমেন্ট বসে আছে আর সকলে 0. I try to find the matrix element, this is equal to lambda times this. ডিটারমিনেন্টটা যেখানে আসবে সেখানে তাহলে একটা ল্যামডা এখানে বসলো একটা ল্যামডা এখানে বসলো সেই, so then therefore lambda square is equal to x square, হ্যাঁ সো এই চেহারাটা হবে and you will find যে এই এটা মানে at the end of the day it will be plus minus I something কারণ we had I k dot r. So at the end of the day it will be এগুলো হচ্ছে plus minus I something, let's call it some omega naught. Say eta will be the here. So this perturbation that will, so this answer is at that order যে f0 equilibrium distribution টা ছিল plus a delta f which looks like e to the power I k z, কারণ I have taken my choice was to take and minus some something times I times something into t. Right? This is the answer. So what is this? It's a propagating wave. It's e to the power I z minus e to the power I k z minus omega t, এখানে omega বেরিয়েছে. So this is e to the power I k z minus omega t. So এটা হচ্ছে একটা propagating wave. Actually calculation টা করে দেখবে যে এটার এটা হচ্ছে 5/3, which is the with kt over m, which is the speed of sound for a monoatomic gas. So you have got the sound wave coming out as the first order. So decay term টা next order এ, কারণ decay term এখানে তো নেই, this is it. I mean at the first order you are going to get only the sound propagating. So that is why you can, I mean that has to be the dominant mode. তাই জন্য তোমরা কথাটা শুনতে পাচ্ছ, ড্যাম্পিং টা যদি ফার্স্ট অর্ডারে আসতো কাঁচকলা শুনতে পেত। So damping টা আসবে next order এ, এইবার second order perturbation theory and with a degenerate situation. So non-trivial, কিন্তু that gives you the viscosity and thermal conductivity. Who are the dampers? তারপরের অর্ডারে জাস্ট এই essentially zeroth order speedটা and the zeroth order damping এগুলো gets modified at the next orders, কিন্তু আর there is nothing physically new. What is physically new is restricted to the first two orders. The first order gives you the traveling sound wave and the second order damps out the wave. Second order a damping, therefore it's much smaller, therefore sound can propagate so that you can hear. So এটা পুরোপুরি প্র্যাকটিক্যাল জিনিস। হ্যাঁ রাইট, কারণ সেকেন্ড ইয়েটা করলে পরেই ওই ইয়ের actually viscosity will come in the form of constants over here. So viscosity টা কত সেটাও বেরিয়ে আসবে। হ্যাঁ রাইট। হ্যাঁ কারণ ম্যাথসের ব্যাপার তো, ম্যাথস ওয়ালারা তো জানতো। হ্যাঁ জাস্ট ম্যাট্রিক্স এর ইয়ের ব্যাপার। সো এইগুলো তো অল দিস যখন থেকে ইলেকট্রোম্যাগ চলছে ম্যাক্সওয়েলের তখন থেকে তো এইগুলো খুব ভালোভাবেই জানা, বা তারা হ্যাঁ রাইট সাইমালটেনিয়াসলি লর্ড রেলে সাউন্ডে করছে, ম্যাক্সওয়েল ইলেকট্রোম্যাগে করছে। সো এগুলো তো জানা ছিল যে কি হচ্ছে, টেকনিক্স গুলো জানা ছিল। So this is the machinery, math machinery to the quantum mechanics এর জন্য ছিল। It was just that the physics will be such strange when you use that math machinery shader. So all right, so that's that. This is it. I mean that is the high point essentially যে বোলসম্যান ট্রান্সপোর্ট ব্যবহার করে মানে the point of doing Boltzmann transport in details was that at the end of the day you have a physical answer. তা নইলে পরে it just looks like মানে তো হলো তো হলো হ্যাঁ। হ্যাঁ এবারে out of if it is genuinely out of equilibrium, see মানে the derivation of Boltzmann transport has nothing to do with perturbation theory, right? So ওটা তো মানে তুমি যদি নন পারটার্বেটিভ সিচুয়েশনে ওটা সলভ করতে পারো তাহলে তো কোনো অসুবিধা মানে you are to home. But the point is যে obviously from the structure you can see যে non perturbative regime ওটা is not so useful, and hence the other developments যেটা Langevin or Fokker-Planck where you can handle it better. All these are the same class of all of them address the same class of problems. Boltzmann, how do you disturb the equilibrium? How do you get back to it? Langevin, if you're not in it, once again, how do you Fokker-Planck? Aki. So they make the same, and those the Fokker-Planck and Langevin are easier to handle. Karan okhane it is not looking at the molecules separate. মানে এখানে তো অ্যাকচুয়ালি মানে ওই কলিশন অপারেটরটা দিয়ে যেতে হচ্ছে না, so even you don't know what under what conditions the solution exists, right? মানে so which I mean যে আজকে মানে সলিউশন এক্সিস্ট কখন তার জন্য যদি এই মানে 30 বছর আগে ফিল্ডস মেডেল পাওয়া যায় তাহলে ইউ রিয়েলাইজ যে মানে it took 100 years plus to establish the solution. When does the solution exist? মানে এগুলো যখন করা হয়েছিল and nobody really worried about it, যে করে দেওয়া যায় যে যেরকম করে দেওয়া হলো and you get an answer and you are happy. কিন্তু then comes the question of in any non-trivial situation you মানে all right, a new situation where things are it's very difficult to handle. But the point is what's important is which we don't really have the it leads to hydrodynamics. মানে just a little bit of another যদি মানে couple of lectures if you would see যে পুরো Navier-Stokes equation ওই everything comes out of this. Langevin হ্যাঁ ওটা এটা এখানে ছেড়ে দিলাম, কিন্তু the point is যে এটা Navier-Stokes equation comes out মানে যদি আমি ইয়ে করে this has its greatness, everything, there you go. A type of প্রচুর মানে that's yeah right. এটা মানে হচ্ছে যে রাইট আগে প্রফেশন